All right, so unfortunately this is really going to suck because both YouTube and our display is really bad today. I can't see anything, so I'm going to have to be craning my necks over the entire time, and I'm going to be recording it instead of live streaming it. It'll be up later today. If you see anything that's off over there that I can't see, just yell it out, please. Otherwise, we are going to continue with the programs that we were looking at, but the last parts of it are going to be discussing variables as well as basic input, output, and best practices. So you saw several variables there called like miles and KMS. Well, both C and Java are what are called statically typed languages. And what that means is simply that when in these languages that are statically typed, you have to declare them before you can use them, right? So for example, over in our Java perspective over here, right? If I wanted to say set miles up here before I've declared it, miles is equal to 10, right? 10 miles, right? That's not going to work because that line comes before the place where I've declared that variable. Not only that, but the variable declaration has two parts, right? You have to declare its name, its identifier, and its type, right? And we're going to go ahead and limit our attention immediately to, or at least in the near term, to integers, doubles, and characters, okay? Where you declare a variable is called its scope, right? A variable has to have a type. The place where you declare it, say over here on, I got rid of it, so line 9 there, miles is declared at line 9. That's where it's born. Here's its lifespan, its scope. It goes all the way to the end of the current code block. So if I try to access it outside of this code block, we'll get to that much later, I'm not going to be able to do that. In fact, I can show you what happens when I artificially change the scope here by just adding some superfluous brackets, right? Now it doesn't know anything about miles. Why? Because it was born on line 10, but at the end of its life, the end of its scope is at line 11 where I've got that closing curly bracket. So let me undo that, but later on we'll have much more, we'll revisit this as we go along because of course we'll have different scopes for different functions and loops and stuff like that. But that's basically how it works. We call it scope. Why? Well, if you're in the submarine, can you see the entire world all the way around? No. You look through the scope and you only see what's immediately in front of you, right? You don't see anything outside of that, even though there's probably a bunch of stuff over there. You can move it around and see, but you can only see within your scope, and that's why it's called scope. For both languages, those three basic types are nearly the same. All right. For an integer, it's oops, sorry. Again, yell at me if I do that, because I can't see it. An integer is a 32-bit 2's complement signed integer. Don't worry about that, right? Those are details that you would have to worry about in, say, computer hardware, right? Later on when you actually do stuff on the system level. But basically know that you can represent 0. You can represent negative numbers and positive numbers in the range of negative 2.147 billion and change all the way up to positive 2.147 billion and change. And why is that? Here's the math behind it, right? I only have 32 bits. A bit is a 0 or a 1. So I can represent yes or no. Well, I need one of those to represent positive or negative, right? So that leaves 31 remaining. Well, base 2 raised to the 31, right? That's the maximum number that I can represent. But because I start at 0, I can only represent up to 2 to the 31st minus 1. In the negative direction, I'm not starting at 0. I'm starting at negative 1. And therefore, I can represent all the way to negative 2 to the 31st. That's why these are different. It's 648 here in the negative and 647 in the positive. Right? If you ever need to do anything larger than that, yeah, you will eventually, but we won't get there until much later. Right? A double is, again, technical here, 64-bit IEEE 754 floating point number. You'll eventually mess with those in computer hardware or whatever. Right? We're not going to mess with those. Instead, we're just going to say, all right, you can represent floating point numbers. In other words, you can represent fractional. Actually, I don't even want to say fractional. Decimal numbers with about 17 digits of accuracy. right? So you are limited here. You can you represent pi out to 1,000,000 spaces? No. You can only represent pi out to about 17 spaces. 3 counts as one of those digits. So you only have, like, say, 15 or 16 digits on the fractional part. If I were to multiply that by 1,000,000, it's not going to get any more accurate, right? It's just going to, the magnitude is going to get larger. This is why we call them floating point numbers. If I would do write 3.14159.6 or whatever, right? I can go ahead and move or float that decimal over by multiplying it by 1,000, right? I have only changed the magnitude. Think about this in terms of scientific notation. This is equal to, let me go into math mode so it looks pretty. There we go. There's math mode. I can represent that as, say, 3.14159 times 10 to the, what would it be, 30? There we go. Right? That's how a number is actually represented. Each one of these parts is a mantissa, an exponent, and a plus and a sign, right? Where this is the mantissa right here, this is the exponent, and then the sign is implicit because it's positive. Again, you'll get into all those details later on. Just know that you have a limitation. You can only represent about 16 to 17 digits of accuracy. Oh, what about a char? Well, a char is a single character. In C, it's an ASCII text character. In Java, it's a full Unicode character. So let me go ahead and open up a web browser here. Did it actually open? There we go. All right. And let's go ahead and go with ASCII table. ASCII table.com. I thought it was. Oh no. Do I not have any ASCII table? Come on. Go, tell me where it is. There it is. All right. So here is the basic ASCII table that predates modern computing by several decades. I think it's in the 40s or 50s or something, under the Truman administration. Come on. This is why YouTube is not working either. We've got terrible network today. Wonderful. Anyway, you can kind of see it partially over here. There we go, finally, something. There are a bunch of non-printable characters. For example, there's a line feed, or right, where's the line feed? There's a line feed. And then there's also a new line. Where is it? I think it's 32. Nope, it's somewhere in there. Anyway, it was born out of electronic typewriters, right? Because there's a difference between a line feed and then a new line, right? Because you can always go vertical line down by rolling that drum. But if you're typing and then you reach the end, right, you can hear that ding, and then you have to physically push it back. That's what those things are there for. In fact, there is a ding in there. There's a bell or alert, right? It represents that. And then later on, of course, you've got your actual printable characters, like a space is value 32. All of them are associated with decimal values over here. And eventually you get into the numbers, 0 through 9. They're in logical order. All uppercase letters, all lowercase letters, and they're all in order as well. This table is set up specifically so that there are lots of little number tricks. If you want to do capitals to lower cases, you only have to flip one bit in the sequence. A whole bunch of other tricks like that. But that's a C's representation of a character. In Java, you have a full character representation using Unicode. I don't know, examples. Unicode you would know as emojis most recently, but also includes CJK fonts, Chinese, Japanese, Korean fonts, right? Because that ASCII text table, they came up with that in the 40s or 50s. And, oh, well, English isn't the only language, right? So they expanded it and expanded it until now we have a full Unicode set where you can do basically any language, ancient hieroglyphics included, but Klingon was excluded. Yeah.
Me and my friend discovered that Discord, if you hold down Alt and then type on the numpad, you can get random characters. I forget which one of those that is.
Yep, and why? Because, again, they are associated with numbers, just larger numbers. Yeah. So if you just type a random number, you might actually hit a Unicode character. Yeah. Like the Unicode smile, right? Or smiley or whatever. Is that it? I can't find an emoji. All right, we've got some terrible network today. So whatever, they're 4725993, whatever it is, right? And there are millions of characters that are still open, right? In fact, anybody can come up with a proposal, submit it. I want this Unicode character. Somebody did and documented their experience because they had stars and filled in stars for ratings. Well, what about a half star? He thought that that should be in there too. So he wrote a proposal and it was ultimately accepted. Right? All right. We are not. Is anybody else having bad network on their stuff right now? Okay. It's just me. All right. So those are full Unicode characters. Don't use Unicode characters in your programs. Don't name your variable the smiley face or anything. Use plain old ASCII. Sometimes it will work, right? But the vast majority of the time, you don't want that stuff in there anyway, right? So those are variables. They have to be declared before you can use them. Well, what about naming them? Best practices for naming. The best practice is the same as before. Follow a consistent naming convention. There are lots of naming conventions. The recommendation is going to be using lower camel casing. Right? So why is it called lower camel casing? Well, look at the first word of a compound word like this. That's going to be all lowercase. Then the subsequent first letter of each subsequent word is going to be uppercase for all variables, both languages. If you want to follow a different convention, that's perfectly fine. Just don't follow a really weird convention. And if you do follow a different convention, you need to be absolutely consistent about it. For example, others would include lower underscore casing, right? This is old school C, right? You have upper underscore casing. Right? And this is casing, there we go. And this is for usually for constants. Right? For example, M underscore pi, remember how we wrote that? Capital M underscore capital P, capital I. That's in both languages, except for in Java, it's going to be just math.pi. We'll look at that in a moment. But constants usually have upper underscore casing. That's the typical way of doing it. You also have upper camel casing, which is typically used in, say, Java class names, right? Names. Right? You can follow other options, but it is not usual, right? Whatever you're going to do, make sure that you are following a consistent naming convention. Be descriptive, right? Bad variable name, for example, bad variable names are foo, bar, baz, right? You'll see those all over the place, but that's just because they need a placeholder. A, B, C, X, Y, variable 1, and then variable 2, right? Var 1, var 2, etc., right? So those are all terrible variable names unless you have a very good reason for doing so. For example, in mathematics, they always call their variables X. Why? Well, because they're doing everything so abstractly that X could be anything. There's no context for X. And so if there's no context for X, you're just say sign of X, right? Then that might be appropriate. But a good variable name will be something descriptive. Good variable names. For example, number of students, right? Miles, kilometers, right? That's a good question there. Generally, avoid abbreviations. Unless, and the question is, why didn't we do kilometers in our program? Why did we do KMS? Well, that's an abbreviation. But in the context, and almost universally, it's understood. Unless the context means that the variable name is well understood, right? And again, the pi. That's been used for hundreds of years to represent 3.14159. That's well understood. Nobody's going to be, at least as long as you know pi, and aren't a complete math, not exposure to math ever, right? You're going to understand what that is. But what if I said, I don't know, psi or something like that. Right? That's a little bit more arcane. What if I said SSN? Most people here will know that that's Social Security number.
Anyone else in the U.S.
Exactly. Not everybody outside the U.S. But so maybe the context, we're not writing it for them. We're writing it for the team here in the United States. What about NUID? You all know that because you all have NUIDs. But anybody outside of the university is probably not going to know that. Maybe the context is okay, maybe it's not. Right? That's where you have to go into the Goldilocks zone, right? Why do we call it the Goldilocks zone? It's just right. It's not too hot. It's not too cold. It's just right. Exactly. Right. So those are some best practices for variable names. Okay. Yeah. Avoid abbreviations. Use descriptive variable names. Definitely do not use, like I said before, bar, baz, whatever. Right. Then we have operators because we actually want to do things with our variables. Right. We have the usual. We have the assignment operator, where you can assign a value or a value of an expression to a variable. The syntax is just simply a single equals sign. Single equals sign. Right. Now you might immediately be saying, well, wait, we already have something like that in algebra. Let's just look at this for context over here. What am I doing on line 22? I'm setting KMS is equal to KMS per mile times miles. Right? This is not an algebraic expression. It's not saying that the thing on the left-hand side is equal to the thing on the right-hand side. It's saying take the thing on the right-hand side, evaluate it, and place it into the variable on the left-hand side. Right? And for some other examples here, we could just say examples. I'm going to go into code mode here. Let's just go see. I can say int a is equal to 10. Later on, if I want to, I can reset that because it is a variable. Why do we call it a variable? Because it can vary. Yeah, I was just going to say vary, but yeah, change, right? A is equal to 20, right? Double is equal, x is equal to, and these are terrible variable names, but we're not representing anything, is equal to 3.5, right? I could do it at the assignment or I could do it later on in the assignment. I could say double y is equal to a times b plus c, right? I could say double xyz is equal to a plus b times c. There's a good question. Right? Why did I say times when I wrote an asterisk? Yeah.
Because if you put x, it's just going to say, oh, x is another.
Yeah, good. X is not an operator, is it? That's a letter, right? But wait a second. In math, what do we do? Oh, hold on to that thought for a second. What about the symbol itself? Mathy, I would do, say, oops, I need to go into math mode here. Times, right? Something that looks like that. Or, what's an alternative? C dot, right? Something that looks like that, right? But do you see those two things on your keyboard? Nope. Why? Because the keyboard was invented hundreds of years before, not hundreds, but maybe 100 or 200, yeah, at least 100 years before the advent of computing. So did they think on putting that stuff onto a typewriter? No, a typewriter is for typing letters, not for typing numbers and stuff like that, right? So they didn't have those things. So what if you fish around on your keyboard, what is the closest thing that's not a letter that looks like one of those things? The asterisk, right? So the asterisk is going to be our multiplication. Plus, minus, those are pretty clear, right? Plus, minus, those are on our keyboards. They thought about that, right? Technically it's a hyphen, but that's still minus. But they did not have that hyphen with two dots, one on top and one on bottom to represent division. So what did they do? Well, they looked around and they thought, okay, well, that's the closest thing, because if you wrote it on one line, it would be x divided by y, right? Or if you wrote it on properly, it would be x over y. But does a keyboard support that? Definitely not. So what did they do? They used that slash there. And is that a forward slash or a backslash? Forward slash. All right. So now tell me about the orders of operations. Let's go back up there, right? Are those going to end up being the same values? Nope, probably not. Well, they could be, depending on what we set A, B, and C to. But why? What's the order of operations here?
A times b.
A times B, because multiplication comes before addition. What about this one over here? Multiplication before addition, so it would be b times c, and then you would add a to it. Right? If we wanted to, you could do something like this: a z. Let's just go t. Right? I can add in a bunch of parentheses. Add in as many parentheses as you want to make it so that the order of operations is well understood, or because you need to. Right? We call that thing what? Yeah.
So I just have kind of a question.
Alright.
Java and C will both automatically understand the order of operations?
Yep, it's universal because now computers don't actually use those operations because it's not efficient at all, right? This is called infix notation, and then order of operations. Computers are way faster using postfix notation. So what happens to your expression is an expression tree is created and then it's rearranged so that it's more efficient. But this is intended for humans, not computers. And we humans have 2,000 years of mathematics under our belt, and we know the order of operations. The order, which is called what? PEMDAS. Right? That stands for parentheses, exponent. What is it? Multiplication, division, addition, and subtraction. In that order, right? So, nice little mnemonic device there to remember PEMDAS rules. All right. Help me write this thing then. What is that thing, first of all?
There's quadratic formula.
Quadratic formula, good. Is there?
It's probably a function thing.
There may be, maybe. If there's not, then just go ahead and write one. Right? So first of all, what about that plus minus?
I have no idea where to find that.
That's not even real math, right? That's just shorthand saying that they're actually two values. So you would need double x1 and double xy2, right? All right, and of course we need our punctuation at the end there. So let's go with the first one, the plus. Well, how do I get a negative b? Negative b in front of it, exactly. Plus, how do I get that square root there?
Couldn't you just put parentheses?
A math function called square root like that. Think back to the 1980s, 70s, 60s, or whatever, right?
And then you can put in parentheses.
Well, first, let's take care of the square root first. SQRT. Why? To save space. For 60 years ago, you were counting hard drive space in literal bytes or kilobytes, or there wasn't any hard drive at all. And if you could save on a few letters here and there, you absolutely did it. But because we don't care about that anymore, right? But because it's there, it's going to be there forever, right? What do I put inside the radical? B squared. How do I do B squared? Yeah, can I do that?
I don't know.
I have no idea.
I can't do that in either language. That means something. That is a bitwise exclusive OR operator. Right? Don't worry about what that means. Just know that that is not the exponent. Yeah, go ahead.
Isn't square root the two multiplication times?
Like, what do you mean? Oh, you mean the exponent like this?
Yeah.
Like that. Some languages allow you to do that. Python is one of them. Is that where you're coming from? Right. So no, that doesn't work here either. That won't even compile. Right? All right. So what do? B times B, right? The Gordian knot. It's just a B squared. So just go B times B. An alternative here is to use yet another math function called power. X raised to the power 2. That it comes in handy if you have something weird like x to the 3.5, right? Then you do need to use that function unless you know some interpolation methods to do it manually, right? I'll go ahead and leave it like that just so that you know that there is this power function there. Minus 4ac, correct? Yeah. That's math, right? That's correct in math world, not in computer science world, programming world. You need explicit operators like that. So I've got the top. Let's just go ahead and go with the bottom here now. Divided by 2 times a. No, I'm not going to make the same mistake there.
Because that would just be 2a, so it would be
Yep.
double.
Yep. But not like that. Like that. correct?
You're gonna wanna put parentheses over everything
Yep.
on the top. So
Top
that's
and
what
bottom,
you use.
right? The numerator and the denominator. Do we remember which one is the numerator, which one is the denominator? The demons are on the bottom, the numerator is on the top.
Never heard that one.
Again, another nice mnemonic device to remember whatever, right? So, I screwed up. There we go. There, now they're balanced. If I had that, of course, the compiler would say, wait a second, there's an unbalanced parenthesis there, I'm not going to compile. That's not valid. All right, great. There's my first solution, and all I need to do is change that to a minus for the second solution. A lot of recomputation here. Maybe I could have put that, like especially the radical, the b squared minus 4ac, square root of that. Maybe I could have put that into another intermediate variable. That's called premature optimization. The compiler will actually do a lot of that for you. Right? Yeah.
Could you have used a float instead of a double?
Oh, yeah. Okay. So I'm not talking about floats because they are just they're only 32-bit floating point numbers. 64-bit floating point numbers, they're less than half as accurate, and they do have their uses. For example, in game development, they prefer that you use floating point numbers because you don't need 64 bits of accuracy to get down to 1 pixel rendering, right? And so floats are a little bit faster, a little bit more performant, but in this class, I'm only going to be covering doubles. Yeah. Oh, sorry. B. Thank you. There we go. Now it's fixed. All right. Thanks. All right. There's another one. What about some invalid operations? What if I try to take the square root of -1?
Well, you would need an imaginary number.
Yeah, exactly. What if I did this? Right? The square root of, sorry, it's not popping down there, is, it's I, right? But in code, ... it is not a number, or nan, right? And what happens when you try to add 1 to something that is not a number? It's still not a number. What happens when you try to multiply it by 5? It's still not a number. What happens when you try to multiply it by 0? Well, anything times 0 is 0, right? No, it's still not a number. So be careful about that. Some others, for example, 1 divided by 0. All right, there we go. What's going to happen there? It could crash entirely. Usually, hopefully, it doesn't crash, right? But this could result in infinity, or negative infinity. And what's 1 plus infinity? What's 1 times infinity? Infinity. Once you've gotten to a nan, not a number, or an infinite number, you're stuck. That's not changing. That's an indication that some arithmetic value or operation that you tried went wrong, right? It could error out. It could throw an exception in Java. We'll talk about the error handling much later. There's another one that's going to be very, very useful, remainder. Right? So for example, you can get the remainder of a number. This is also called mod or modulo, right? By using the % sign. So let's just look at some examples here. Now, if I were to take 10 and divide it by 3, of course, we all know that that's going to be 3.333333 off to infinity. Computers are not infinite. Right? They cannot represent infinite sequences of numbers like that. So normally that's what you would get, 3.33 something, right? But this is a little bit different, right? This is going to be division with remainder. So go back to grade school now when you did not have fractional values. When you try to divide 10 by 3, right, you have something that looks like this. 3 goes into 10 3 times, and then what did you write up here at the right? R1, because that's a remainder of 1. We don't know how to do that yet in grade school, right? So sometimes you want that. This is going to result in 1 because the remainder is 1. What if I said 10 mod or modulo, or 10, excuse me, mod, I don't know, 2 results in 0 because there is no remainder. It evenly goes into it. What if I said 10 mod 4? Oh, careful. It's always going to be an integer. So what's the remainder of dividing by 2, it's going to be 2, right? Or dividing by 4, excuse me, right? Here's the trick, right? How can you tell if a number is even? Mod by 2. A mod 2
If it
would be
1.
0, right? Odd would be 1. All right, good. So that's going to be a trick later on when we do some conditionals, determining if something is evenly divisible by 2. In other words, is it even or odd? It works with any modulo. So if a remainder of 3, divide by 3, a remainder can be 0, 1, or 2, right? Then what happens? You go right back to 0, right? Because now it's divisible by 3 again. Let's see. Default values, right? So if I just create a variable, let's go with C here, int a. What value does a have at that point in the program? Oh, careful, this is C. Right? So hold on to that thought for Java for a second.
Is it going to be null undefined?
It's what? Undefined. C has no default values. Right? It could be anything. Right? So as a consequence, it is best practice to initialize your variables. Right? For example, going back to C here, int a is equal to 10. Or if you really wanted to guarantee a default value of 0, then you'd have to do it explicitly. Now, 9 times out of 10, the compiler is going to save you from yourself and put in a default value of 0. However, there is that 1 time out of 100 or 1 time out of 10 that they intentionally put in some flag value to indicate uninitialized memory, like dead beef. There we go. There it is. See, there is no default value for uninitialized variables, thus it could be garbage values. In fact, we could say, well, the default value is going to be dead beef. That's a clear and huge signal, red flag to you that this is uninitialized memory. This is an uninitialized value. Again, 9 times out of 10, or 9 times out of 100, if you want to malaphorism there, then it's going to be 0. But there's that one time where somebody does something different for a purpose and does dead beef. Why do we say dead beef here? That's hex speak, right? So you can spell a lot of stuff with just A through F and then 0 through 9 using leet speak. And one of those things is dead beef. There are these magic numbers everywhere that people come up with. You can do baseball, all right? You can't do football.
T.
Yeah, T. You can't get a T. Oh well.
7 kind of works.
7. Yeah. Okay. Yeah.
Just put that.
Something like that. But anyway, dead beef. What about Java? In Java, uninitialized values are not allowed. Let me prove it to you. Let's come back over here. I've lost my CS50 IDE, but that's fine. Let's go ahead and go with int x. Okay. Int b is equal to a x times a, 10. That red means what?
It
Does not compile, right? Because an uninitialized value is not allowed, right? So let's go ahead and read it, if you can read it really quick. The local variable may not have been initialized. In fact, it was not initialized, so we're not even going to compile for you. See, this would compile, this would run. You might get 0, you might get dead beef, you might get 1, you might get some rando value out there. So make sure that you're always initializing your variables in both languages. Okay. Somebody did, a couple of people did observe null, right? In Java, class values may have a null default value, right? That's actually not true of local variables. For example, if I go back over here to my Java and go, instead of int, I'll go big I integer x, right? I still can't do it. Int y is equal to x times 10. That's an uninitialized value still, right? So it's not going to take on a null value here, but even if it does, now it will compile, but what's going to happen when I try to run this program? It won't run because what's null times 10? Null ain't any number I ever heard of. So it's going to be, that's invalid. I'm going to throw an exception at you. Just like if I divided by 0, it would also throw some sort of an exception back in my face like this. So you do have to use default, you do have to initialize even these values here to, I don't know, 5. There, now it'll run just perfectly fine. I can find my play button. There we go. All right, and then, of course, it's going on to the rest of the program here. You can stop a program over here with this stop button. All right. In the context of a class, but not local variables. Right? So I just mentioned, I don't usually mention that, but two of you observed that there is null. There is null in both languages, but they're not exactly the same. We'll get to that later. Question? No? Anybody? All right. So here's another pitfall. Default values are one thing, but here's another pitfall called truncation. So consider the following code. We'll just keep it with C, but it's the same in both languages. Int x is equal to 10, y is equal to 20, double z is equal to x divided by y. Predict what's going to happen there. Come on. I've got to end the code block. There we go. Predict what's going to happen there. What value does z take on? 0.5? That sounds logical because it's 10 divided by 20. Let's go ahead and try it in the only thing that's working right now. Where's my demo code? There we go. Let's just go ahead and do it over here in the demo code. There we go. And instead of printing out that message, let's go ahead and print out Z. 0. What happened to my half? Right? It got truncated. Truncation means, okay, yes, for the purposes of division, it's going to be 0.5. But an integer divided by an integer has to be an integer. So we're going to take that period, cut it, and throw the rest of it away. It's not rounded down. It's not rounded up. It is truncated. It is just thrown away. It could have been 0.99999, and it still would have been cut off and thrown away. It wouldn't have been rounded up or anything. Right? So the takeaway here is both languages do this. In fact, any statically typed language is going to end up doing this. The result of an integer times, plus, or minus, and division, and let me go ahead and put all of that into one code, must be an integer. Now with those other three, you're not going to have a problem. 5 times 5, 25, that's going to be an integer. Integer times an integer is always an integer. Plus, minus, same thing. Integer times, plus, minus, it's going to end up being an integer. For consistency purposes, division also ends up having to be an integer. Right? Yeah?
If you did something like 22 divided by 10, would that result in 2 then?
22 divided by 10, yep. 22 divided by 10.
Is the answer 2.2?
Because what's going to happen, it's going to be 2.2, but the 0.2 gets chopped off. 2.0. Right? It is a double number, right? Because z is a double. Right? It can hold 2.2. It's just that the result of that operation on line 8 has to be an integer. Right? And so consequently, you have a loss of data there. Must be an integer. So the fractional part is chopped off and thrown away. Thank you. Sorry. There we go. Okay. So what's the solution here? Sometimes you do want to preserve the fractional part. Right? So what you do is typecast. Right? Typecasting means, let me go ahead and just steal this code from before. What I'm going to do is I'm going to put in front of at least one of them a double. Right? So all I've done there is said, for the purposes of this x divided by y operation, treat y like a double. In other words, don't treat it like 20, treat it like 20.0, excuse me. Now the result is going to be 0.5. And then when we take 0.5 and place it into the variable on the right-hand side, we're good to go. Let's go ahead and look at that in Java. The C would be exactly the same. Again, this is called typecasting, explicit typecasting. There we go. Did I do something wrong? Nope. Okay, there we go. What's wrong?
Nothing.
Okay, that worked. What was that pop-up?
I just want you to save it.
Oh, you can turn on autosave. Apparently I don't have that on, but yeah, you can turn on autosave in Eclipse. It's not worth it to dive into where that is located, but whatever.
Will Z be a double if either like X or Y is a double? Right?
If you changed one of these to a double, then you would not need
Yeah.
this explicit typecast,
Okay.
right? So you might be asking yourself immediately with that question is, well, then why do we use integers at all? I can only do up to 2.147 billion anyway. They seem really, really limited, so I'll just do doubles and everything. Nope. Optimization is one reason, but another reason is that not everything is a double, right? If, for example, in the real world, in the math world, I should say, if I take 1/3, which is 0.333333 repeated forever, and I add it 3 times, 1/3, 1/3, 1/3. In math, what do you get? 1. But in computer science and computers, you don't have this infinite representation. It might be 0.33333332, 3333334, or it just gets cut off, 33333 and then 0 after that. Well, what's 0.333333 added 3 times? It's 0.999999. Right? You get into floating point errors like that, you don't have that kind of precision. Right? So sometimes you absolutely do need integers. Right? You still need integers because their integers are exact. You are never going to get 1 plus 5 is suddenly 6.00009 or something. Right? So integers still have their use and their place. Let's go back up here. All right, so we've been doing a lot. Those are the basic operations. Of course, there might be other operations later on. But let's talk about input-output, because that's what we have in our program, right? Let me now switch back over here to our input-output program and get rid of this stuff. Right? Unfortunately, I can't run the C right now because I've lost my internet, whatever. Right? So please enter the number of miles. Here, when I type, it's going to be in green because the standard input is in green. The standard output is in black. And then the standard error is red because warning, 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 something went wrong. Right? You saw that when we saw that exception. Right? It was printed in red. That's just Eclipse highlighting it in red to get your attention that something went wrong. So 45, I don't know. I only ran 5 miles this morning. There we go. So I ran 8.045 kilometers, right? By the way, as an aside here, if you're interested, we run a monthly Run with School of Computing 5K just around the campus. That'll be on the first Wednesday of every month. So next Wednesday at 3:30 p.m. Meet right outside of shore. And it's going to be 86 degrees or so, so dress lightly and bring your sunscreen because I'm sure that it'll be blazing. So if you're anybody cross country, 1, 2, all right, want to continue cross country? All right, so anyway, there's the interactive program. Well, first of all, how did I get the input? We used a scanner. How did I get the output? We used this. We used a system.out.printf. Let's talk about the output first. Let's go back to the notes over here. All right. Output in both languages can be done using printf. System.out.printf or in C, just printf. The F stands for formatted, right? You can provide a formatted string, and it will print to the standard output, right? Input is done with scanf, and that's going to be the standard input, which is, of course, your keyboard. For both languages, you have a placeholder, right? You can use placeholders to determine what the variable is that will be formatted. Let's just go ahead and take a look at this one over here. %F is one placeholder. That's not going to be, you note here that it didn't print out % anything, right? That is a placeholder that's saying I'm going to print a floating point number, a fractional number. That's why it's 5.00000. There's another F, right? %F for the other one. Now, instead of taking printing out %F, what does it do? It takes these variables over here, formats them, and then replaces this %F right here with the value that's formatted. Likewise, KMS will do for % over here. There are 2 placeholders, 2 variables. the order matches. Right? It's not going to go randomly like backwards or anything like that. The first placeholder is the first variable, the second placeholder is the second variable, etc. Yeah.
If you, for example, at the end of that code got rid of kilometers, would it print miles or 5.00 twice?
In Java,
Can we just say
error,
Okay.
lots of red. In
Don't
C,
do that.
yeah, don't do that. And in C, it will compile, it will run, but garbage results, dead beef results. Yep. Yeah.
So would you have to put miles, comma, miles?
If you wanted it printed twice,
Okay.
yeah, miles. You're just printing this, but that's not the correct program, right? Right. Yeah.
So in C, would like the first one be miles and the second one would be deadbeat, right? 'Cause that-
Something like that, yeah. It might actually end up printing out 0 or whatever memory location it defaults to, and then whatever garbage was in that memory location converted that into a number representation, right? Or a very good implementation will say, that's probably not a memory location you should be messing with. I'm going to go ahead and destroy your entire program and kill it, right? We want that to happen, right? We don't want arbitrary access to memory locations for anybody. But otherwise, as we've seen, there's already one placeholder. This is both languages, by the way, because I was demonstrating this in Java. %f is for floating point numbers. For integers, it would make sense if it's %i, because I for integer, but it doesn't. It's %d for digit, I think it is, for integers. The one that does make sense, however, right, that seems kind of backwards, right? For d for doubles, it should be d, right, instead, but no, it's f for floating point numbers. %c for characters, char values. Right? That's the only one that makes sense, right? There are dozens and dozens and dozens of placeholders. You could read all about them if you want to. Every language. This is printf, by the way, is almost as universal as a main. Even Python will support it in a way, right? It uses kind of this syntax, not exactly this syntax, but every language is going to have a printf style formatting that you can use. Right? The default for floating point numbers is to print 6 decimals of accuracy. Right? Alternatively, you can use other modifiers to print more, less, etc., or even fancier stuff. So, for example, here's the format. X %y f. There we go. That's what I wanted. Where x is the minimum number of columns, and y is the number of digits of accuracy. And I should modify the above, including the decimal. All right? So you can use two numbers. You don't have, both are optional. Both x and y are optional. Let me just go ahead and show you an example here. For example, let's go ahead and print out pi in Java. So let's go back over to the demo. All right. Now here we're printing %ln, and we can go math.pi. There we go. And we can print out pi, and what is its default value? That. It's going out as many digits as it has in the number. But what we can do is we can modify this and not use println, system.out.printf, and we can give it a placeholder value here. If just %f is going to be math.pi. There we go. That's going to be 6 digits of accuracy, right? Because that's the default. Well, what if I only want, say, 2 decimals of accuracy, or 4 decimals of accuracy? Or you know what? Let's go ahead and go out with 40 decimals of accuracy. Right? Then I'm only going to get, come on, 2 decimals, oh, come on. All right, so there's not println there, so what do I have to put at the end to make it look nice? /n/n/n.
Those are 2 decimals.
Oh, darn it. Thanks, ITS, for coming by to fix it. Did I do it? There we go. 2, 4. Oh, what happened there? It only had 17 digits of accuracy. In fact, count those up. Remember, a double only has 17 decimals of accuracy. So what happens after that? I don't know what it is, a bunch of zeros. If I were to do this in C, I'd actually probably get a bunch of garbage instead of a bunch of zeros. Zeros is better than garbage, trust me. But here I'm getting a bunch of zeros. Now let's just do one last one here, and then we'll pick it up on Wednesday because there's no Monday for Labor Day. But let's go ahead and print out, I don't know, just 2 decimals of accuracy. But let's use that other number now, that X, 10. All right. What that's going to do is it's going to print out a minimum of 10 columns. Well, if you want 2 digits of accuracy, that's 2. The period, the decimal counts, and then there's a 3 in there. So what's left over? 6. 6 columns will be padded out on the left-hand side here. Right. Why would you want something like that? Well, take a look at any ledger book. All the decimals are lined up, right? And if you want to get things looking nice and neat in your output, then you need to format it like this. Yeah?
Does it apply in the opposite direction? Like, if you put a certain number of
Good question. We would do that in on Wednesday. It's not exactly this, but what if I go negative? Then it'll justify it to the left. Save it. Is there a quick key for run? There. And you can't see them because they're a bunch of blanks, right? But then you can also do, like I said, there are dozens and dozens of placeholders. There are also dozens and dozens of modifiers. So if I go 0, 10, there we go. Instead of spaces, it's going to pad it out with zeros. And I don't know if that's what satisfies your curiosity, but you can do stuff like that. Why would you want to do something like that? Very rarely. But think about your NUID. Anybody has NUID starts with a 0? 10% of you should have a 10, right, yeah, there we go. 10% of you should have an NUID that begins with a 0. Sometimes you do want leading zeros because it's not a number, it's an identifier. Okay. All right, like I said, hopefully that, yeah, we got good recording here. Go ahead and stop.